Welcome back to another lesson. This video will introduce the notion of a perceptron, applying what we've learned about classification problems and linear boundaries. The perceptron is essentially going to represent the same equations we just discussed, in a different structure. Let's move forward to understand what that really means. A perceptron is the most basic building block of a neural network. It is essentially a single layer network with an input layer and an output layer. A perceptron is a binary classifier that takes input data, applies an algorithm to this data, and then outputs a binary value of either 0 or 1. The binary output represents specifically defined data classes. As in our case, a 0 would imply a non-diabetic patient, and a 1 would imply a diabetic patient. We have an empty perceptron in front of us right now, so let's begin filling it in. The input layer takes in known data, such as the age of a patient and the blood glucose level of a patient. As mentioned prior, the age of the patient can be represented with x1, and then blood glucose level can be represented with x2. The final node in the input layer is usually called the bias term, which is typically set to 1. This seemingly arbitrary choice will become more clear as we move forward. Having dealt with the first layer, let's move along the network to understand the other components of a perceptron. Let's bring our focus to these lines that connect our input layer to our output layer. These lines have a parameter called the weight. Each line has a respective weight value, and here we will label the first line W1, and the second line W2, the third line will be B. These weight values can be adjusted to control the performance of the perceptron. This brings us to the final output layer of the perceptron. In our simple binary classification case, this perceptron only contains a single output node. This output node is where we put everything together to obtain a function binary classifier. Let's bring our focus to the single output node. This node has two main functions. The first function of this node is to understand the input data that it is receiving. It does so by taking a weighted sum of the input that it receives. This ends up giving us a very similar equation to the one we saw prior, multiplying x1 by its respective weight value W1, x2 by W2, and finally the bias term by B. This equation gives us the sum of the input that the output node is receiving. As you can see, by selecting the weight and bias values appropriately, we can obtain the exact same classifier that we discussed earlier. This node now has a mathematical expression for expressing the summation of the input that it receives. The second function of this output node is to take this total input value and output it as a binary 1 or 0. For this, we are going to use the following step function. The following plot shows the step function. The step function is a very simple type of activation function that takes a certain input. If the input value is positive or 0, then the step function outputs a 1. If the input value is negative, then the step function outputs a 0. When we incorporate this function into our output node, we refer to it as an activation function. There are a variety of activation functions, some that we will discuss further in the lecture. However, for now, the step function is all we need. So, in summary, the output node gets the weighted sum of all inputs as a single input value. This input value is then fed through an activation function to get the appropriate output. In our case, this activation function is the step function. The step function converts our input combination of health parameters and node weights into a binary classification. In essence, this is the role of a basic perceptron unit. An additional note about the perceptron is that it is not limited to only 2 input values, along with a bias term. In fact, you can have as many input parameters as you deem relevant. For example, we could add an additional input node. Labeling it x3 could represent an additional health parameter for our patient, such as the body mass index for a patient. This would result in a more complex input equation. We can add as many input nodes as we want, each with their respective weight connection. This results in an increasing number of terms inside of our resulting equation. In order to keep this equation consistent and simplified, we can simply write the equation in vector form, where x is a column vector containing all the x parameters, and w is a row vector containing all the respective weight values. We will use this simplified vector form equation moving forward. That concludes the Perceptron lesson. I hope you guys enjoyed getting your first real introduction to neural networks. There is more on the way, so I'll see you guys at the next lecture.